It's like worked out. Yeah. So when you go like it's like I speak like you're in it's like
Well, hello everyone. Thanks for braving the snowstorm outside to come here, and nice to see so many people who've made it through the road conditions today. And yeah, welcome to McKenzie Miller's Defense. McKenzie is originally from Ohio and came to us a way of North Carolina, where she did a bachelor's degree in geology at UNC Charlotte. And while she was there, she worked on a lot of sort of related topics, and also received some fellowships along the way, backpacked the lower 48, and spent a semester in France. And also did some internships in exploration geology. So when she came up here in December of 2023, she was really prepared and eager to get working on the geology of Alaska. And when she arrived in summer 2023, she immediately went to the field, which kind of set the tone for a lot of work that she's been doing here. McKenzie made some forays into working on pogo and contributed to some papers on the Denali Fault. But her main topic was about southeastern Alaska, working in the area around Juneau, and spending several field seasons there, several weeks in the field to do some extensive detailed mapping, and make lots of measurements, structural geology measurements, and take a bunch of samples that she analyzed, and that's what she's going to present today. Besides the geology, McKenzie's also spent a lot of time exploring Alaska on foot, hiking and climbing her way across the state. And she's also a great artist, and has painted a lot of Alaska scenery, including the picture of a field area that's on the poster. And so, like, painting the subject of your geologic study shows some real dedication to the science and an ability to think about things in not just one way, but lots of different ways. And so McKenzie's been a fantastic student over the last 10 years, and has done a lot of really great science in southeastern Alaska, and really brought everything together to come up with a new geologic model for the evolution of southeastern Alaska, which is going to present to us today. So I think that's what we're all waiting for. So without further ado, take it away.
Thanks, folks. Thanks. Yeah, I can't believe I've been here for almost 3 years now. Time flies. And now I guess I get to talk about what I've been doing, which at first didn't feel like a lot, but then I put together this slideshow, and I think I guess it was kind of a lot. So excited. Well, the title of my thesis is the Monazite Chronology and Field Study of an Inverted Peruvian Metamorphic Sequence in the Coast Mountains of Alaska. And I have to say that when I started here, I did have a bachelor's in geology, I swear, but I did not really know what about half of those words meant. So if you're kind of like this is a lot of buzzwords, you're in good company. But I'm going to break it down, so it'll hopefully become comprehensible and we can dive into the science and have a little bit of fun. But yeah, I just want to thank off the bat my committee. They were so important for getting me to this point. It's been really amazing. All right. Yay. And just again to talk about it, there's going to be kind of a little overview at the beginning where I try to bring in like the non-technical people in the room, like my parents who don't have geology degrees but are smart. So hopefully we'll get everybody to enjoy this, and then I'll have a little bit of some technical background about the geologic history of the area, and then a bit of a dense methods and results section. I'm sorry, I hope it's fun. You can get something from it, and then some quick conclusions and kind of wrapping it all up. And I do want to say in this slide as well, just feel like the context of what is a successful master's. When I came here, I wanted to do a master's that had field mapping and structural geology, but also like some intense analytical work like geochronology and geochemistry. And I think this ended up fitting the bill. So see what you think. Oh, and that's me and Helen for our field season this year, having some fun in the rain. Sort of like rephrasing the title here, but the question my thesis is asking is how did an inverted Barrovian metamorphic sequence form at the boundary between insular superterrain in North America and Juneau, Alaska? So you can break this down into two parts. The first kind of meaty part of this question is what is an inverted Barrovian metamorphic sequence? So that's kind of a geologic question, and the second part is our geologic setting. For this question, what is an inverted Barrovian metamorphic sequence? If you haven't taken a geology class in a while, there are three rock types, right? There's sedimentary and igneous, and the third rock type is metamorphic rocks. These are the rocks that are forming when mountain belts are forming. So when any of these other types of rocks are buried to great depths and experience high pressures and temperatures, the minerals and textures and chemistry of the rock will actually change to suit those conditions and be thermodynamically stable. And that gives us some really pretty rocks like gneiss and schist and slate. Barrovian metamorphism is the specific series of rocks and minerals that you expect to see in a continent-continent collisional zone. So these are our most familiar metamorphic rocks. They reflect increasing pressures and temperatures with increasing depth in the crust. So your deepest rocks are going to reflect the highest pressures. Like if you think about it, as you go deeper in the crust, it's getting hotter. You have more rocks sitting on top of you. So those are rocks like gneisses, migmatites. Then in the mid crust, you have schists that might be like amphibolite grade, and then in the lowest crust, like closest to the surface, you have your slates and phyllites. So if you were to turn this upside down from what you expect, that would be an inverted metamorphic system. So in this situation, this is still representing the surface of the Earth here. You would have like your hottest, highest grade rocks like migmatites and gneisses sitting closest to the surface, and then your shallowest or coolest kind of rocks, your phyllites and slates, sitting in the like deepest reaches of your metamorphic sequence. And you might already be thinking, like, how could this form? This doesn't seem that crazy, but it's kind of crazy. So we'll talk about how that formed. How do we know that this is inverted? Like, how can you even tell what is up and down in metamorphic rocks? They're kind of weird. They're kind of hard to look at. Well, when metamorphic rocks form, the randomly oriented minerals that are in the section will orient perpendicular to the directions of maximum stress. So as you're like burying rocks and they're getting squished, cooked by all the overlying rock, all these platy minerals, the micas that make schists so shiny, those are aligning perpendicular to those stresses. So when you actually get a pile of rocks, it looks like this. You can see these bedding surfaces. These are not sedimentary beds. These are foliations. Shouldn't have said that. These are foliations. So the directions of maximum stress are like this and like this on these rocks. So you can kind of get a sense for what these foliations look like and tell that this would have been the upside here and this would have been the downside. So now that you're armed with this information, you can tell what is right side up and what is upside down, or what is right side up versus down in your rock. Then if you map the metamorphic minerals in your section, you can see which direction your metamorphic grade is increasing in. Is it going up as you go up in the section or up as you go down in the section? You would expect it to go up as you go down. So again, you're looking for hotter rocks as you go deeper. In metamorphic land, mapping minerals like this is called isograd mapping, which just means saying grade. Grade is like slang in metamorphic land for how hot the rocks were and high pressure. In Juneau, the mapped isograds, and in most places where Barrovian metamorphism is mapped, isograds that are commonly mapped will include garnet, which this is kind of hard to see, but like these little red guys are garnets. If you don't remember what those are, starlight, which is an aluminosilicate polymorph that makes these nice, well, it's not a polymorph, but it's an aluminosilicate that makes these nice crosses. Kyanite, which is a true aluminosilicate that is very blue, and then silmonite, which is an aluminosilicate, silvery and fibrous. And you would expect this to be kind of like the coolest, Okay, cool. Garnet comes in around here. This is a petrogenetic grid, which is showing us if you took a soup of elements and subjected them to certain pressures and temperatures, what minerals would you get? So at the bottom, you would start to see some garnet. Like this is correlating to a temperature of about 575 maybe degrees Celsius where garnet is starting to form. And then you would expect starlight to start to form at a slightly higher temperature. That's what this reaction line is saying. And then you're starting to lose starlight at this slightly higher temperature. And then the polymorph change between silmonite and kyanite is kind of on this like diagonal line, so it's controlled a little bit by pressure by temperature. So this is all the background to say, if you find these cool looking minerals, you can get a sense for where you were in pressure and temperature space when your rock formed. And thus, you can tell if your inverted, if your metamorphic sequence is inverted. So some guys did that in 1973 in Juneau. Juneau is like here, and this is the ridge that I did my study on. This is like those colors you hike up enough. So the isograds start down here. This is like, we'll go over this again. This is like super low grade rock, kind of some green schist, then you get your green schist, and garnet comes in here, and then kyanite, and then starlight somewhere like this, and then silmonite comes in. So they decided that this was an inverted metamorphic sequence based on this mapping, which is cool. So now we know that we have this inverted metamorphic sequence. Where is it? It's at the boundary between the insular superterranean and North America, which you can find in Juneau. You can also find throughout the coast mountains in Alaska. So this is, again, also for people not in Alaska watching. The coast mountains run from like the northern tip of Washington all the way up the coast of like BC, a little bit of Yukon, and into Alaska. So it's a huge mountain belt. That's more or less where I was. Just in the top half of it in Juneau. Geologically, this is what that looks like. Alaska is a patchwork of terrains. So the insular superterranean is the largest terrain to accrete to North America throughout the old accretionary or orogeny process. Insular is these terrains here in purple. So lines up more or less with those coast mountains we were just looking at. The other terrains all here have been accreted prior to the accretion of insular. So picture them like terrains are little fragments of crust. They're kind of like groceries on the conveyor belt, and they all pile up the end of the conveyor belt. Alaska is the end of the conveyor belt. These guys in green and blue had already been accreted prior to insular. And then there is this big pink batholith that is called the complex. The rocks are not actually pink, sorry, the maps. But anyways, it's a batholith, kind of akin to the Sierra Nevada batholith, that exists more or less between insular and North America, so probably formed by the subduction zone that would have accreted insular terrain. So anyways, that's where we're at. There's a lot of stuff you can get into with this, but I'm gonna move forward and you can ask questions if you want. I do really like this stuff. Here I just highlighted like that boundary zone between insular and North America. Zooming in on my field area, it's like a pretty cool postage stamp that represents this suture zone because you've got purple, like the colors are about the same from this map to this map. Purple is representing insular superterranean or insular superterranean affiliated sediments in this case. And then the green is representing peri-Laurentian rocks, or rocks that have already been accreted to North America. They're probably correlated to the Yukon-Tanana terrain here. But these are metamorphic rocks that got squished and deformed by the collision of insular to North America. So we're in the right spot to look at what that collision looked like, geologically speaking. And just in the northeastern section of my field area, like up here as the glaciers start to come in, so we did not go there, there is something called the Great Tonalite Sill, which is a really long, thin tonalitic sill that exists across the western margin of the Coast Plutonic Complex. In this area, it's dated really well. It's 72 million years ago by a Garrels paper. So we're in this like great postage stamp to study this. We know what our question is. How do we form an inverted metamorphic sequence? We're in a good spot to do that. Why bother? Sometimes it's a question I ask myself doing like academic geology. Like this is definitely not a thing that most people think about every day, but it's pretty cool. I think it's important to understand how our processes work, right? Just because we live here and it's cool to understand. So with that said, these kinds of upside down inverted Barovian metamorphic sequences are found globally, most notably in the Himalaya and other collisional origins, but there is no real agreement on a thermomechanical model for how they form. People have said all kinds of different things. A really common one would be like, what if it's an overturned antiform? But there's really no evidence for that. We'll get into that in a bit, but there's not a simple explanation that really ties it all together for any of these places. So it's kind of exciting. We've got one sort of in our backyard-ish, more or less. So might as well go study it. And then Juneau is an area, like this whole insular superterranean North America collisional belt is an area of tectonic controversy. So providing some good geochron and structural data is always a good thing to like help bolster models that are competing between people that don't actually look at the rocks. So it's like good to sometimes go look at the rocks. And lastly, I do have like an economic geology interest. Shout out to Marisa. I didn't really do anything with that with the study, but there's the historical Juneau orogenic gold belt is located in the footwall of my study area. So the fluids and metamorphic goodness that came out of this section did end up causing some pretty significant gold mineralization. So it's kind of cool to like think about how those processes might have been intertwined. Cool. So now we get into like a little bit of the more technical bits. Sorry. So some possible models for inverted metamorphic sequences like that we wanted to test with this study are the hot iron model and a sort of structural tectonic inversion. It's helpful to go into these kinds of studies with some models that you plan on testing instead of just being like, I don't know, we're going to go see what we see, because then it's kind of overwhelming and you don't know what to focus on. So we honed in on a couple models since these sequences exist globally, lots of people have put in a lot of brain time thinking about how they think they might have formed. So a lot of models exist. I picked the ones that seem to have the most support and are kind of like the broadest. The hot iron model is sort of intuitive. It's this idea that you might, like, if these little blocks are representing a little crustal cross section. In the first bit, we're like pre-inversion. This is like the white is representing cool crust and the gray is warmer crust that's deeper. And this is saying like if you added a heat source such as a melt to the very top of your section, that would begin to heat it from the top down. This would probably result in like pure shear throughout the sequence, which is just like kind of sandwich flattening, no intense sliding or asymmetry. And you would expect sort of a consistent age metamorphism across the sequence. This model does have some issues, which we can talk about, but it's kind of intuitive. So that was one that I thought would be interesting, especially because we do have a big intrusion sitting right on top of this whole belt. So it kind of makes you think like, well, didn't they just get heated by that thing? Isn't that why it looks like this? The other sort of possible model that I thought seemed pretty viable would be a structural or tectonic inversion, which is to say that you had a series of thrust faults. They could have been ductile thrusts, so like little shear zones, but thrust faulting that would have placed deeper crust over successively shallower crust in like little slices, kind of like a deck of cards sliding. If each card is like a little disparate crust slice and they all slide and you get deeper sitting on top shallower. This we would expect to see something called myelinitic texture throughout the sequence, which is just this like really fine-grained asymmetrical sequence sort of texture. It like looks like your rocks have been sheared. Like you could just tell. I swear. There's scientific bits that you could just tell. And then you would expect, if you were able to date metamorphism, that you would have sort of younging ages as you go down in the sequence, because the deepest rocks that have been shoved up would have been shoved up first. So those would have the oldest ages, and here, and then it'd be younger, 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 and younger. So with that in mind, we've got some like pretty good predictions that we're going out into the field with to see if any of this tracks. And the methods that I use, as I was saying at the beginning, I wanted to do field mapping. So in order to kind of test these models, we had field things that we wanted to test. We wanted to look and see if there was any obvious like brittle faults that just juxtapose these different crustal levels, or if there are like really obvious little shear zones, or if it all looks really homogeneous. And then after that, we take samples of the rock and orient thin sections back to the lab and do microstructural analysis, which is just, it's petrography, but you're really honing in on the textures that you see in the rocks to see how they've been deformed. And then finally, we did some thermochron and petrochron to look at when the rocks were beginning to exhume and if there were patterns in exhumation ages across the sequence. That's what the thermochron is telling us. And then geochron, which is the monazite uranium lead petrochronology, that is a way of dating when did metamorphism deformation occur in these rocks directly by measuring the decay of uranium isotopes and lead isotopes. So, in the field, we had some fun sometimes. Is it Alex having a good time? I think. And then also we had some rough times. I didn't really take a lot of footage of like actual field mapping, but what you do is try not to get super wet. You take a lot of structural measurements, so all those foliations I was talking about, you measure those with either a compass or an iPad, and then take a lot of like lithologic observations or looking constantly at the rock types that we're in just to see what's going on. And what we ended up doing was making a little geological strip map. So this is my ridge. I took out the like topo lines because it made it too noisy, but this is a very steep ridge. This is the middle part. All the stuff inside is tree. We hiked up approximately like this with the trees, and then up across the ridge, up until about we couldn't continue anymore because of glaciers. And first, I did kind of an updated lithological mapping situation because the lithology map, which is the rock type, that mapping was kind of large scale zoomed out, so all of this just was mapped as like schist, which is fine. It's more or less true, but when it comes to looking for metamorphic minerals, they only really form, like those index minerals I was talking about earlier, those only really form in metapolitic rocks, which is like old slates basically that have been metamorphosed. So it's sort of like worth noting, if most of the sequence was not actually metapolitic, then it'd be like really hard to actually tell there was a perfect sequence. So we did some mapping, found some lenses of marble. This stuff down here is kind of phyllite, maybe lowest grade schist. The light greens are some marble lenses, a couple diorite lenses, some like true amphibolite hornblende rich rocks, and then a couple pink. These little lenses here are little fingers of that tonalite sill. When you have a magma intrusion, it doesn't have to just go to one spot. It'll like exploit little weaknesses in the crust and have little offshoots. So these are a couple offshoots of that. And then the other thing I did is look really hard to remap the isograds that were mapped in 1973, because the whole project is based on these isograds being real. Interesting. So at the base of the section, there's a sumdum fault. That's like a brittle fault that's full of quartz. That's where the Juneau orogenic belt lives. So that's a real fault. You can't see it in like a regular field campaign. It's just mostly been drilled out by mining, but it is real. So that's there. We know that's there. And then walking up, I looked like really hard at the garnet. The garnet section is easy to see. Those are those little red guys. Super easy to find. So the garnet in icegrad. This is mine in black. This is the dashed one, is what was previously mapped. So mine in black more or less matched where they had theirs. And then what I really wanted to find was starlight, because it's cool. It makes those crosses. I wanted to see that. I thought that'd be really nice. It's also pretty fundamental to showing this progression in like metamorphic reactions getting hotter and hotter throughout the sequence. I was not able to find starlight, not even in thin section, so that was kind of a bummer. And then I did find the kyanite in icegrad, which was pretty exciting. It's those blue guys, again, that blue mineral. So that was pretty sick. Looks like cool rock. It's very blue. I don't know why I don't have a picture of it, but I swear it's real. What's interesting is that when we took that into a thin section, there's actually sillimanite coexisting with the kyanite, so I don't think it's fair to say that this is a kyanite icegrad. I call it a kyanite sillimanite icegrad. And then that's it. The whole mapping where isograds leave is sort of difficult because these aluminosilicates are not at all continuous throughout the sequence. You'll find them in like little teeny little outcrops. So saying when they stop existing is a pretty challenging endeavor. So I did not do that because I'm not a fan of it. The other thing we did that you can see in this map is structural mapping. This is a much reduced number, but it did a bunch of strikes and dips of all the foliations to see if there were any trends across the sequence. There were not. All of the foliations more or less dipped 40 degrees, like a moderate dip off to the east-northeast. So didn't really tell us a whole lot, except for that this doesn't have evidence of being like in the limb of an anticline or something where you would expect some steepening or shallowing of these strikes and dips. It pretty much looks like this if you're going to make a cross section of it, which it did. So this matches up here to here. This is no exaggeration for the vertical extent of the ridge. So down here I have the kind of phyllites, and then they strike and dip. Like there is some variability, but when you're drawing a cross section, you want to kind of average it when they're not super meaningful. So I just sort of projected these different units down into the subsurface. And this is also showing like in space where all the samples I took are. So you can see they're pretty well spread out throughout the sequence. And anywhere like in here where there's not a ton of samples, there either was no outcrop or there just was no outcrop. We sampled everything a lot. But that's pretty cool. And you can sort of see here like the tonalite. I wanted to draw attention to this. The tonalite is concordant with the underlying foliations. So that's not traditionally how you think of an intrusion. Typically, you think of an intrusion as just blasting through whatever rock it's going through and not matching anything. But this is concordant with the underlying foliations, which is interesting and indicates that it was being deformed at the same time. So kind of cool. At the same time as the schist, I mean, which is all of this. So now we get to do a little tour of the rocks to prove that fieldwork did actually happen, and rocks are fun, so we're going to look at them. In this lowermost part of the section, there's these phyllites, look kind of like this. Maybe look rich, just kind of up to your discretion on that one, but it's super crumbly and crappy, but you can take really good measurements. I mean, you can still see here like really well-defined foliation. And this is definitely a pretty low-grade rock, so that's cool. Then moving up, like kind of pass through a super boggy section of trail where there isn't a lot of outcrop, and then all of a sudden you're in garnet land. So we've moved up into amphibolic grade rocks. That kind of gunky section is the fault. Some fault. So these rocks, these are garnets here. Really nice dodecahedrons. This is kind of a garnet schist, maybe nice, but probably schist. And then here's some steeper dipping foliation surfaces that kind of indicate more or less how these rocks look. Here's some more examples of how these rocks in the middle of the section look. Just like really well foliated, super easy to take measurements on. This thing's really cool. There's a big quartz apatite dike kind of situation. And this is the overall metamorphic rock foliation. So this dike would have been treated very straight like this, and then been squished and accordioned to look like that in a ductile setting. So can't really do much to analyze that, but you can look at it. Like, that's cool. And that got squished for sure. Moving up a little bit more, we get into some nices. So even if you're not a super fan of like the ice grad mapping, you can't deny like these are certainly higher grade rocks than the rocks that are below them. Got a little bit of partial melt happening and like super well defined bands, and definitely ductile flow happening here. And like I have just ridiculous banding. Like it's like a barcode. Alex, look down. Finally, these last rock pictures. We've got, this is sort of the overall character of the contact between the schists and this overlying tonalite. It's all kind of oxidized and blasted, but It's all still deep dipping the same exact way, and you can't really tell even in this picture where the contact is because it's just it all looks the same zoomed out. Like the tonalite is really well foliated. This is a really close-up look at the tonalite contact with the underlying schist, or gneiss. You can see it follows foliation and is deformed in the exact same way. So, what did we walk away from these weeks in the field with? We didn't find any obvious brittle faulting or like myelinitic shear zones, so we didn't find evidence for like structural juxtaposition of these different crustal slices, not at least at a macro scale. We found consistent foliation strikes and dips, so that is not consistent with any kind of like, if you had out of sequence thrusting, even in a ductile setting, I think you would expect some steepening as you go up section. Didn't see that. I think you'd also expect a similar pattern if this was like the overturned limb of an antiform, like a big giant fold. So we didn't find any of that, so it seems like those aren't really viable options. And it was difficult to locate starlight isograd, so the whole like isograd mapping thing I think is worth revisiting by someone maybe eventually. So next we take our little chunks of rock back to the lab, cut tiny slices of them, and shine polarized light through them. And they look really cool like this. So these thin sections are about the size of a domino. I don't think you can really see the scale bar, but these are like domino-sized bricks of rock that are blown up here. And this is just how they look. There's no color correction happening. So this is an example of one of my samples from down at near the garnet in isograd, so kind of the lowest part of the section. This is one of the most interesting rocks to look at, even though it's kind of gray. This one has what we would call like proto-myelinitic or maybe myelinitic texture, which is to say it's pretty fine grained. That's why it kind of looks gray and fuzzy. Those are all the quartz grains. They're pretty small. And it has garnets here, and like they show up as black isotropic, but highlighted them here. And then the other thing this has is that evidence of like simple shear hard deck sliding. It's kind of hard to see, but this is a shear band here that shows if you flip the sample to show how it's actually oriented, this is reverse sense shearing. So when I looked at that, it was like, oh, all right, cool. This is a structural story, case closed. Maybe it's hard to see it at the field scale, but when you look at a microscope, like all the rocks are going to look like this. But in fact, most of them did not look like that. When you walked like a half a kilometer further up section, the grains got a lot coarser. We've got, this is the rock that I thought was the kyanite in isograd, the first time you see kyanite ever. And it has both selenite here and kyanite. So that was where I got that from. And that's about here in the section, so it's moved from like here to here. And then moving up, the rest of the rocks pretty much look like this, which is very pretty, but kind of dull. The black things are still garnets. The pinks, these are those aligned micas forming a foliation, and the background, like these grays and blues and whites, are quartz. So you can see that the quartz is actually pretty coarse grained. Kind of looks like it hasn't been sheared to help. If anything, like it has a foliation, so it certainly has experienced pure shear flattening just from above, but there's not really any other exciting stuff. And here's another example, another sample that looks more or less the same. So that was like most of what these samples look like. It's kind of a bummer because as a geologist, you really want to see those aluminosilicates. They're really cool and fun and pretty, and they mostly were not present in these rocks to look at. So got really used to these ones. Finally, the foliated tonalite, I did take one sample from that just to have, so you can sort of compare and contrast. This is what an igneous or like just an igneous rock that's been deformed a bit looks like. So it's much coarser grained. It does still have foliation though, so you can, and it's hard to see here, but there is evidence of reverse sense shearing in this tonalite. So this is sort of just for fun, because I don't know. It's like a lot less fun for me to just say what I thought about the thin sections, and a lot more fun to have everyone look at them. But the takeaways for me were that we had that kind of card deck sliding simple shear going on just down here around the garnet in isograd, which is not that far from the Sumdum fault, which is a reverse sense brittle fault. So to me, it was kind of like these could be related. And then the majority of the section, like all of this stuff, is that kind of regular looking pure shear stuff. So it's just showing regular flattening, it's not showing any like intense deformation. Yeah, still no signs of starlight even in thin section, so that was a bummer. And overall, I'd say the assemblages here show regional contact metamorphic signatures. Like we don't see any minerals that would be definitive evidence of contact metamorphism. Like cordierite would be kind of a hallmark, or maybe some intense muscovite growth, but we don't see any of that. So that's sort of inconclusive with regards to like the role of the tonalite in forming the sequence. Now to the fun part. So with all of that kind of more fundamental science done, did thermochron and geochron. So the argon lab here is run by Florian. It's awesome, state of the art. And so of course I wanted to use it. It dates when a rock cools more or less below 300 degrees Celsius, just to ballpark it for you. So that's when you're moving up below like 10 kilometers across. So your rocks are on their way up. They're not being buried and tortured anymore. So you could also say it's the beginning of uplifting cooling. Did a lot of like, to do this, you take your rocks, crush them, you separate out the minerals that would include potassium, which will decay into argon, and then you irradiate those, and then you run them through the mass spectrometer. We just get to look at the numbers stuff, because Florian helped me do a lot of that. Anyways, so here we are. This axis more or less correlates to this axis. So these samples are these, and these are our results. I also plotted up some old results of somebody else that did argon in this area, actually potassium argon, but a similar method, just to see if they would kind of play nicely together, and they did. Also I wanted to point out, or like reiterate, the available geochronology that did exist in this area before. It's just that the tonalite silt is 72 million years old, based on zircon uranium blend. And the Sumdum fault was active about 55 million years ago. That's with argon on white mica that formed in the fault gouge, or in the fault zone. So those are the dates that we have, and everything else here was a mystery until we did this. So the argon ages, the age of exhumation for this bulk of the section here is about 55 to 60 million years ago. So a little bit of time after tonalite silt was intruded. And in this lowermost part of the section, we did grab a couple ages, and those are a bit older. So like this lowermost part of the section was actually getting close to the surface, or moving up from about 70 to 65 million years ago. So that's kind of interesting. It's kind of cool to see like a break in ages more or less across the fault. That always feels good, like compelling. It's good stuff. So those are the takeaways from that. And next, we did monazite petrochronology. So this was like the meat and potatoes of the work that I did in my master's. Monazite petrochronology is just a method for dating approximately when did metamorphism and deformation occur in your rock. And you do that by using the same systematics you use for zircon. So you measure the decay of uranium into lead. What's nifty about monazite is that it has, well, the chemistry is pretty reactive. So whatever is going on in your bulk rock chemistry as it relates to like metamorphic reactions will be reflected by your monazite. So if you measure uranium, lead, and trace elements in your monazite at the same exact time, you can get a sense for like how old is this monazite and what conditions did it form under, which is great if you're trying to figure out what metamorphic stuff was going on. And this is just like a little sad face that I thought was funny when we were doing this. So how do you do monazite petrochronology? I'll run through it pretty quick, but first, this is where I mostly worked with Nate. You do electron microprobe maps of your thin sections. So these are those domino slices of rock. And we're going to locate the monazite grains, which is really hard because they're really, really tiny. They're like 10 microns big, so they're minuscule. So you map 5 different elements across like your entire thin section. The one that is helpful for finding monazite is cerium because it's a rare earth element mineral. So if you do that, you just get a black screen with like these tiny white pixels, and if you zoom in on those white pixels, you find monazite grains, and then you can do like a more fine scaled map of each grain to see what they're looking like. And they look like this in probe images. They're kind of these like black and white blobs. In this instance, you're also mapping for different mineral or elements. The most useful one for monazite that I found was mapping yttrium. That revealed these kind of darker cores, more or less, and lighter rims. Not all the time, but there's sort of a pattern there. That's always interesting. The light is representing a higher concentration of yttrium, and the dark is a lower concentration of yttrium. So now we know where the monazite grains live in our thin sections. We know what each grain looks like. And so it's time to travel to your nearest laser ablation split spectrometry facility. So that was in Santa Barbara, which was a huge bummer. We went there and used the McKenzie equipment, which are mass spectrometers, which allow you to measure the massive, super tiny amounts of elements. So what you do is you take your grain maps that you have and place 8-micron spots on the grains. So these little blue rings are representing what a laser spot would be. So you like have your thin section, you locate where all these little spots are going to go, you place them on the sections around the grains, and then you let the laser do its thing. The laser shoots these spots and it ablates material. That material gets shot down the mass spectrometer, and you measure the uranium, lead, a bunch of trace elements, all kinds of goodies. So you really get a lot out of these tiny little grains. These are what the mass spectrometers like. So the split stream one, we got a bunch of collectors, and this is the uranium lead one. It's only got 4 collectors, maybe 5. And what that gives you is a crap ton of data, which is cool. I will say, like, not to toot my own horn, but this was sort of a different monazite study than the ones that I've seen. They typically have like 4 or 5 samples and like a lot less spots, which makes it a little easier to kind of wave your arms about what all these numbers mean. But I had 12 samples that I did this on and like about 60 spots per sample. So it sort of was like data overload, but I kind of think an elegant story came out ultimately. So for each sample, we did plots like this. The first plot is a Terra-Wasserberg plot. That's just telling you if your uranium lead systematics are working. Like, do your ages make any sense? Are they concordant? Are they going to fall off this line? So we did that first. I won't get into that too much. But then, if you're like satisfied that your ages are legit, you go and make a mean squared weighted deviation plot, which is a much friendlier way to look at this information. So in this plot, age in millions of years is on the y-axis, and you've got just the spot number on the x-axis. So each of these represents the age of a spot from a monazite, and length of the bar correlates to the error associated with that. So you can't say for sure, like with random error and some other things, that this spot is going to be like 62 million years old, but you're like, it's 62 million years old plus or minus 3. So we did that for all the spots, and what ended up being really interesting was to color the spots by yttrium concentration. So again, that was the concentration of yttrium in that monazite grain as it was ablated. And darker colors are representing high concentrations of yttrium, the lighter are representing low. And it's not a perfect correlation, but you can see if you squint your eyes a little bit, like the top ages, these oldest ones, closer to 70, those are pretty light colors. And then there's sort of a gradient, and then darker colors at the most young ages. So that's pretty cool. And as it turns out, this trend was present in pretty much every single sample, and so is this range of ages. So when you get like this sort of range of ages, a ranked age plot they call it, sometimes people are inclined to say, well, that's not a real like progression of ages, because if you rank all of them by like how old they are, of course you're going to get kind of like a little slope here. But I would argue that this is a legitimate correlation between the age and the chemistry, because there's this trend that we see. So I think this is a legitimate trend in ages that we're seeing, like a progression that is from oldest to youngest. So with that in mind, I did not feel like it was good scientific practice to to try to arbitrarily pick an old age and a young age, or try to put one line through all these ages, because then it wouldn't really be very meaningful. So, with the help of Florian, who's way better at coding than I am, we came up with this way of plotting all of the ages. So each of these is representing a sample's worth of ages, and this is kind of like a kernel density plot that is typically used in detrital zircon, but instead we applied it to monazite. So each of these violins is representing all of the ages and how they're distributed in a sample. So oldest up top and youngest ages down here, and the widest part represents the highest concentration of ages. So just kind of looking at it, don't really see a downward younging or any distinct age populations. There's some sort of swirly stuff here where some of them only have young ages, some of them only have old, but these are right next to each other and they contain the entire spectrum of ages available. So the way that I've ended up interpreting this data is that there is just a range of ages that is present across the entire sequence. So the oldest is more around 72 million years old, and the youngest is about 58 million years old. So based on that spectrum of yttrium yttrium concentrations we were seeing, and this spectrum of ages, I would say that monazite was growing in a prograde metamorphic environment at around 72 million years ago, and then was immediately beginning to exhume and cool and enter retrograde conditions until 58 million years ago, when things cooled off enough that monazite was no longer growing. So these are some pretty cool ages because they line up really well with the ages that already exist in the area. So again, that tonalite is 72 million years old, and the fault at the base of the sequence is 55 million years old. And if you remember in the last slide, all of that argon stuff is showing us that this whole sequence was exhumed at about 55 million years old, which is only a few million years after 58. So this is kind of showing us this rapid transition from prograde metamorphism into exhumation. Things got buried and then they immediately shot back up to the surface. So that's a pretty cool finding. Now we get to go back to the models and ponder how all of the data points that we have collected fit or don't fit with any of them. So start with the hot iron model. What worked and what didn't work based on what we saw. The tonalite is 72 million years old, and the monazite prograde age started about 72 million years old across the sequence. So that's pretty compelling for the tonalite being the hot iron, as it were, the heat engine responsible for this metamorphism. But we don't really see contact metamorphic minerals, and the tonalite itself was intruded at 12 kilobars, so it doesn't really jive that would have been above green schist facies rocks. There has to be something else at play. You can't just the rocks sitting underneath rocks at 12 kilobars are super high grade already, so you're not gonna be sitting on top of green schist. The tectonic inversion, that was wrong bullet. For the tectonic inversion, we would have expected to see downward younging throughout the sequence, so that violin plot would have had a slope to it, but that really didn't happen. So, so that's incompatible, and then the compatible side is that we did see some reverse sense deformation in the sequence, I would say. But neither of these models really fit to a T. I felt like both of them, those inconsistencies were high enough that kind of makes you wonder. So I ended up, Marisa sent me this paper sort of late in my thesis, and I was like, oh wow, this kind of is a great point. What if this was a hybrid model with channel flow, which is a model that's been proposed in the Himalaya before many times, but also debunked in the Himalaya. In the Himalaya, they're no, we see the structural downward younging in all of our ages, so that's a structural inversion. But we did not see that. So worth revisiting the whole channel flow idea, which says that you would have, this is again, our upright metamorphic sequence. And then as a hot channel of mid-crust just extrudes in a compressed environment, you would get an upside down sequence of rocks that doesn't have like internal faults in it. It's like squeezed out like taffy. That's kind of cool. So I made a schematic thermal model of that. Won't make us sit there too long, so I get a little long-winded, but basically at 72 million years old, we have, sorry, also this is like thermal kind of thing here on the left, and this is more of a tectonic block model, so whichever suits you better look at, or if you hate all this, don't look. Sorry. At 72 million years old, we've got this tonalite intruding, so that would be like a big red hot thermal anomaly in the crust, and then underneath of it, you would expect to have some prograde metamorphism, and if there was a channel flow that extruded, so the blocks are pressing together, and there's this like hot, no shear strength tonalite sitting here, there would be like an extrusion of a hot blob of crust underneath of it, and that is where we would see our inverted metamorphic sequence. And this is kind of cool because it fits with a lot of different things. I mean, one of the things about this model is that it would expect a coherent block of amphibolites grade crust bounded by reverse set shear in the footwall and some detachment in the hanging wall. I didn't talk about that earlier, but there is a known detachment just to the east of this, like up section, that nobody's really done much with, but it's kind of like, okay, so we do have that. Like you have an extrusion and then this hanging wall is dropping off of it as a detachment. And then you would see some ductile reverse sense shearing down here at the lowermost part of your extruded channel, which we do have. Remember that deformed, sheared up rock from the garnet in ice grab. And the other prediction of this model is that everything would be like being buried and then exhumed within pretty rapid succession, which is what we see between the Monazite and the argon data. What else is good about this? I thought this was cool because it provides an example where how the tonalite would provide a heat engine, so it would be like popping off those 72 million year old Monazite ages, but it's not like just a static blob of magma that's supposed to be sitting on top of these things. Like it incorporates the dynamic nature of the system and how the tonalite is foliated and deformed as well. And yeah, I thought this was overall cool because it kind of also explains this hybrid regional metamorphic / nearly static contact metamorphic thing that we're seeing. Like all of the minerals are regional metamorphic. We don't see like cordierite and things like that, but we do have to consider that this tonalite was important because of it being there in the ages. So this is a model that I thought was worth considering. I'm not gonna like tell anybody you have to like take that home and hang on the wall. It's just kind of interesting because there's nothing in our sequence that doesn't fit with that. The only problem with that model is that overall the scientific community is kind of like suspect of it. So kind of cool. Overall, what we can take away from this, like what is actually going to matter from this work for anybody else. I mean, this is new geochron in an area that is relatively poorly studied, despite being like a 5-minute drive from the state's capital. So what we can say from our Monazite data is that the Monazite, or this sequence at the collisional zone between insular superterranean and North America underwent prograde to retrograde metamorphism 72 to 58 billion years ago, which immediately postdates the tonalite sill intrusion. This is all true. And the sequence exhumed below argon blocking temperatures by about 55 million years ago in the amphibolites grade portion, which is consistent with the timing of fluid flow and exhumation that's indicated on the well-studied summed up fault in the footwall. So all this is good stuff. It's all jiving, everything's working together. And then the final thing is that with regards to like regional controversies, there's always ongoing debate about the timing of insular's accretion to North America. I don't think this like disproves or really changes anything, but it's another piece of evidence that metamorphism and collisional related deformation was continuing in the Suture zone well beyond just the initial collapse of the overlap basins. Frequently, the age of insular accretion is attributed to the age of basin collapse based on detrital zircon, which is really cool and great, but it's about 90 million years ago, and most people are like, oh, you can't have metamorphism continuing until 70 million or 60 million years ago, but I mean, why not? Origins take a long time. You have a basin collapse and then continued collision for tens of millions of years. I think this is just like the hot tail end of the collision. And one more thing, with regards to the models, like I was saying, you can't exactly definitively say like that my channel flow model is it. I wouldn't take it, don't take it to the bank, but we can say that you should not take the structural model to the bank. Like, definitely don't take that one. It's gonna bounce. The ages and the texture do not match with the structural juxtaposition. The hot iron model without any structural component really doesn't work either. And the channel flow could be viable. And then I do want to throw in at the end, like, I would like to acknowledge that you could also reevaluate this geogradient inversion by like remapping the isograds and doing some more intensive thermobarometry along the whole sequence. I think it's possible that you would find that this is just a coherent block of amphibole rock that's been thrust above green schist rocks on brittle subdump fault, in which case it wouldn't really be an inverted metamorphic. Well, maybe it would be an inverted metamorphic sequence side. That's a further discussion. But it could be like a way simpler explanation, I guess, if you reevaluated the PT conditions. So, with all that said, that's all the project. And you can ask me, I wanted to ask myself, I guess, as I was wrapping this up, like, was this a success? Because eventually you get the weeds and you're like, I can't like prove or disprove these models. Is this worth it? I think it was good. It was a great learning experience. I got to do all the things that I wanted to do in a master's. And it's been super helpful. I felt like it prepared me for whatever, if I wanted to do more academic research or to go into industry. So that's all really good. It's like kind of huge also to feel pretty good about disproving a model. Like the structural model is being implicated frequently. So it's kind of good to be able to say, hey, like you should rethink that thing. And this definitely provides some like high quality geochron and structural data with like regard to the insular superterranean accretion event, which continues to be controversial. So yeah, that's pretty much it. Next I want to say thanks. These are some pictures to start saying thanks. These are like whatever my more professional school pics. Here's me and Marisa and Florian looking at core and Pogo. I don't know if you guys knew we had that picture. Me and Wyatt running from a helicopter and outside of Kashmir. This is a staged photo. And here's like once the grad students revamped the grad student field trip up to the Berks Ranch this year, and that was a real treat. Really glad to have done my time here as a grad student, not prison, grad school. And I did make a list on my phone of everybody I want to thank that kind of got out of hand. There's a lot of people. So I want to say thanks, especially, oh my gosh, mostly haven't been stuttering. I say thanks especially to my committee, Marisa, Florian, and Nate. I have learned a lot from you all, whether it's in classes or working on this project. Thanks so much for helping me. Yeah, there's more to like at some point with masters, you gotta just do it, and I wouldn't have done it without you guys. Thanks Johan for looking at my metamorphic rocks with me and for teaching me one-on-one how to do metamorphic microstructure in my first semester here. I was like, wow, this is crazy. I've never seen any of this stuff. Got to see it. I want to thank my field assistants, Helen and Alex, who had variable amounts of suffering in Juneau with me. I hope that it was fun to some degree. I would think other grad students throughout the year, so there's a whole bunch. Sean Marvel introduced me to Alaska fieldwork when I first got here, and like sort of shepherded me and did all that. I've had a lot of great people and friends around. So thanks, Josh. You can watch my cat a bunch. Claire's watched my cat a bunch. Snowshoes, watch my cat a bunch. Like, a lot of people watch my cat. My favorite guy ever, he's up there. I want to thank him. He's Wilson, named for the Wilson continent cycle. He's awesome, and he needs people. He's very, very social. Everybody else, like Ozzy, thanks so much, and Indy and Celine, and oh my god, I'm gonna forget people. I'm so scared. Kira, and of course Claire. It's been like great. Other players, there's 2 players. Both players have been really amazing in my life. Oh my god, I'm gonna miss people. Thanks to my non-UAS, still geology friends. Tyler here, and to Sandra, Jess, and a bunch of you guys. Thanks, Grant, for also watching my shadows and doing outdoor adventures with me. Sorry, I'm not forgetting it, but I'm getting kind of out of time here. And I want to thank my brother who came visited one time, took that cool picture, and my parents who taught me how to love geology and tell stories. So I hope that this just I'm proud. And one more thing, and I want to thank all the geology mentors I've had over the years. Some of them might be on Zoom. I'm not sure who all made it, but my old boss when I worked in Nevada for that summer in exploration, he was like, "You should go do a master's," and it's like been like 5 years, but I did it, Andy. Thank you. Yeah, I think that's it. Thank you all so much. If you have any questions, yeah.
I have a question, McKenzie. Congratulations.
First of all, good job, McKenzie.
Thank you.
Second, I would say that the channel flow model is not only viable, I would say probable in that area based on the faults, based on where the migmatites are, based on your, I don't know what monazite ages mean, but thermoporosity as well. Super valid. I think you see them in a lot more places, not just in Himalayas. Got a paper right now that's in review for one in New England on one of the terrains, so I wouldn't be surprised. As soon as I saw it up there, I was like, "Oh, that's channel flow."
Really?
Told Mike that, so would not be surprised. The other thing, what do you think your just question-wise that decreasing yttrium value in all of your monazites?
I was hoping someone would ask. I think so. It's the yttrium is lowest in the center of the monazite, or like it's the lowest in the oldest stages, and then the yttrium increases as you get younger. I think it's because I'll just say what I think first. Garnet is the biggest heavy rare earth element sink in metamorphic rocks, aside from xenotime. So if garnet is destabilizing, like if retrograde metamorphism is starting, like things are still moving around elementally, but the garnet's no longer happy, I think it's gonna release yttrium. So this is like really common practice in monazite petrified land. That's like what everybody hangs their hat on. They're like, yttrium's going up, garnet is dying. Like that's what's happening. I'd say my committee, who's not from monazite petrified land, was very suspect of this. Rightfully so, and we did do some garnet mapping to try to look and see if you could like catch any of that. I mean, the rims of the garnets are grungy, so you at least got that. But
Zoning?
There's zoning, but you can't see zoning in the yttrium. That is kind of like a brain break for me, because it's like, well, if the garnet broke down, you wouldn't see the low yttrium anymore. It just would be gone from the garnet. So I don't know, but a lot of people have agreed on this conclusion. Whether or not it's accurate is for someone else's opinion.
I think if you've got other breakdown products of garnet as well.
Yeah.
Breakdown.
Yeah, I mean, you see all of the heavy rare earths in the monazite go up as the ages get younger. Yttrium is just kind of the easiest one to look at. Yes.
Excellent job. Congratulations. I have a question about tonalite. So I'm wondering, just in your opinion, or if there's something in the literature, when do you go from a quote unquote foliated tonalite to an orthogneiss? Because if a tonalite is foliated, is it really a pluton anymore?
What an important question. Well, I think that this one, the reason that still call it kind of a Pluton is because it's very narrow. It's like about 10 kilometers wide at the max. But if you get to like the upper half of it, it's not foliated. It's just the base of it that's foliated. So like the top is still like very plutonic in character, and then it gradually becomes foliated. It would have been cool to go look at it, but it was like up in the glaciers.
Gotcha.
So I'll leave that to the people.
Cool. Thanks.
Yes.
Okay, two questions. First, could it be that the rock that you call like proto-monazite or monazite, because it's relatively low grade, get these relatively large garnets? Could it be that it's fine grained because it's a low grade rock and not really that deformed? Monolithic, I mean, the shear band's fine, but doesn't.
Yes, I would think so. Well, the garnets are let's look at this, but the garnets are bigger, so I guess I sort of extrapolate and say, well, the garnets are bigger and it would take me a while to click back to it, but I think I can.
Well, they can be, you can have garnets in low grade phyllites. But the
That's true.
polymus is fine grained, but you still get porphyroblasts.
It could be so. I would say if that could be true, that it's not biologic, because it's just low grade. There's several samples that look like this, so whatever this was a pattern.
Because that's a problem with
Yeah.
these
Finalized.
lower grade rocks. If it were like a schist and then suddenly it's fine grained, yeah, okay, you could
Yeah,
say it's monolithic, but here I'd be a bit cautious.
that's true. Pretty much all of these lower samples.
I try to take away that you have shear bands and the
Yeah.
deformation. It's just that the whole rock fabric might not be monolithic. Oh, got it.
I would agree with that. I guess I was inclined to like interpret it as biologic because it had the shear bands, but it could just be shear bands.
And a second question. You didn't find starlight, didn't find quarterite. Really lovely to have quarterite, because then you have a good argument for contact metamorphism.
I agree.
But both minerals, starlight and quarterite, are really dependent on the oral geochemistry.
It's true.
If there's not enough magnesium, you may not get quarterite. Do you have any whole rock geochem where you can say, yeah, there should be quarterite, but it's not there because the chemistry is favorable, but it's not there. So then the same with sterilizing.
Right. I don't have full rock geochemistry.
Absence of it is not necessary in arguments.
Right. I guess the only reason I think you're correct. I think doing geochem and doing vector genetic modeling would have been a smart thing to do, but I didn't.
Well, it's only so much you can do.
But yes, I agree with
This
that.
wasn't meant to be criticism, it was just.
I did only bring up starlight so much because they mapped it with such confidence.
I know we
Like-
talked about this.
Yeah, and it's like, well, there's only so many outcrops of this ridge, and I think we looked at all of them, and we certainly tried to sample all of them. So if there was starlight, it was cryptic, and we missed it, and
Yeah.
it was only going to be visible in sections. So that's the only reason I mentioned it, because I think if you go back to this guy, like, this is fun. This is part but I think that you just have garnet, kyanite, silmonite. This does not really constrain your BT conditions. Like, you're kind of in here. Like, it's not like, I don't know, if you had like cordierite or something that like really puts you over here into the hot part of the temperature path, like it's sort of a loose definition here. Are there any questions coming in on Zoom?
Yeah, I was gonna say, quick question, just based off people on Zoom, and you might have partially answered it, but Sean Marble had a question. About you weren't able to find starlight despite being previously mapped. Do you know what those original observations were based on? And why do you think you were unable to find it?
I think it's a great question. It's 1973, so they didn't like. Well, I don't know if people would have done this, but they did not publish the coordinates of like where they obtained their samples. They just said that they did this section work. My hunch is that they found it on a different ridge and then just like continued the line. Because there are several ridges that are the same. They mapped them as inverted metamorphic or like they mapped the ice crowds up to over on this ridge and down on this ridge, and they had helicopters. So one of my feelings is that like I felt like so much that Helen thought and Alex thought he looked at every damn rock that existed up there, but we maybe would have looked even more at every rock if we had a helicopter and one of the ridges. Yeah. We did backpack down with like 60 or 70 pound backpacks. Yes, and they.
So if your like channel theory is correct and the tonalite still like came up and you're seeing the kind of underside of it, could you expect to see the other side of it in outcrop like several kilometers away?
Yeah.
Would that prove or disprove your theory possibly?
Yes. I think it would, like, you would want to see the detachments, like this is the part like the tonalite and the underlying rocks are like reverse faulting, and then there's gonna be extensional detachment. Thanks for coming, guys. On the top, like you said, a few kilometers up section. That's in the ice field, so people have done mapping like there is whatever knowledge of a detachment fault up there, but I didn't get to go see it. We could, like, you know, we'd be on a rope team, we could go do that, but I'm not gonna lie, if I went to the Juneau ice scale on a rope team, I think I would just want to go have fun. It'd be really like hard to pack all your stuff up there for that and rocks too. But yes, I think you could expect to see that. So that's testable. Yes.
I feel like I can't be the only person thinking this, but do you know the origin of why that fault is named Some Dumb Fault?
Funny story, I just started a job at Fort Knox, the gold mine town, which is cool, and like I gave this presentation to them in like the worst format. It was like an hour of me rambling, it was terrible, and the like tech who's like 21, he was like sitting there on his phone the whole time. I was like, wow, I can't believe this guy. And he was like Googling everything I was saying, so he got to the bottom of this. And it's named after like three things back, with like a glacier and then a fall and then a whatever. But originally the reason it's named that is because some European guy, some white guy, like misunderstood a native dude who was telling he was like, go to the Sondam Glacier, which is supposed to sound kind of like the sound of ice crashing, and he misheard it and said Sondam, so it's Sondam down.
All right, well, we will probably cut it off. Thanks, everybody. If you have follow-up questions, maybe come to Black Spruce later. I think McKenzie might be there.
Yeah.
That's a good place to discuss them. I do believe Beleda had a question online, but maybe Beleda can follow up with the email. And or she'll be here soon enough as we discuss.
Yeah.
So.
I'll be over.
She would be what she would say is the question. Wow.